Alejandro Felix, and this is my gas laws project. So the common conversions: to go from Celsius to kelvins, you add 273.15, and that's how you got kelvins. And to go from kelvins to Celsius, you subtract 273.15. And these are the conversions to go to get atmospheres from pascals, kilopascals, millimeters of mercury, and torr. So 1 atmosphere is equivalent to 760 millimeters of mercury. 1 atmosphere is equivalent to 101,325 pascals. 1 atmosphere is equivalent to 101.325 kilopascals, and 1 atmosphere is equivalent to 760 torr. So the first law we're going to introduce is Boyle's law, which states that at a constant temperature, the volume of a given mass of a dry gas is inversely proportional to its pressure. So if the volume increases, the pressure decreases. So some history around it was that it was first discovered by Robert Boyle, but later his studies were confirmed by other researchers who conducted experiments between the pressure and volume, and this was all during the 17th century. So this all had to revolve around his experiments, their experiments in total, like they revolved around air, which they believed was an essential element, which it is. So the equation, so it's pressure, the first initial pressure, multiplied by the second the first initial volume, and then equals second pressure, and then second volume. And a real life example would be your tires being more flatter in the morning because of the cooler temperature. And here it shows the graph representation of how the higher pressure led to a decrease in volume. So this here is a video of practice problems, including about Boyle's law. And then here's the question. So Boyle's law has to do with question number 4, which states that a sample of nitrogen at 40 degrees Celsius was compressed from 400 milliliters to 0.460 milliliters, and its new pressure was found to be 400 pascals. So what was the original pressure in kilopascals? So this problem is an example of Boyle's law because it deals with pressure and volume, and it's also a before and after. So the conversions would be going from pascals to kilopascals, which is equivalent to 0.4 kilopascals. This would be the equation. X is the pressure, the unknown pressure, multiplied 400 milliliters equals 0.4 kilopascals times 0.460 milliliters. And so after you multiply that together, it's 400 milliliters equals to 0.184 kilopascals, and then you divide it by 400 to get kilopascals, and your answer would be 0.00046 kilopascals. And here's the experiment I did on Boyle's law.
So my first experiment is on Boyle's law, which basically states that at a constant temperature, the volume of a given mass of a dry gas is inversely proportional to its pressure. So this has to do with pressure and volume, and I'll be demonstrating this with a water bottle and 2 balloons, and I cut the other balloon in half so that I could put it on here, and then I also put a hole here so for the pressure, and this is how it's going to be demonstrated. So as seen from this, the balloon basically inflated more. So this basically demonstrated that as volume increases, so does the pressure here, as from Boyle's law.
So the next law I'm going to introduce is Charles' law, which states that a gas expands as the temperature increases, so it's vice versa. A decrease in temperature would be a decrease in volume. And the history was that it was named after Jacques Charles, but credited and confirmed by Gay-Lussac. And the graph representation, basically, it shows how the temperature is increasing and so is the volume. And the equation would be the initial volume over the initial temperature, and then it would be the final volume over the final absolute temperature. And a real life example would be like a basketball that's left out in the cold weather and it would shrink in volume. And this link to YouTube sends you to some practice problems based on Charles' law. And the question here that correlates with Charles' law is question number 2, and then which states that what is the final volume if 3.4 liters of nitrogen gas at 400 kelvins is cooled at 37 degrees Celsius and kept at the same pressure. So this question demonstrates the before and after, and also includes an initial and final volume and an initial temperature and final volume. And then the only thing that would be converted would be from going to 37 degrees Celsius to kelvins. So it would be 310.15 kelvins, and then the known volume, a known variable would be the final volume. And this would be the equation here: 3.4 liters over 400 kelvins equals the final the unknown final volume over the temperature, 310.15 kelvins, which after being cross multiplied is 1054.5. You'd cancel out the kelvins to get liters, and over 400 kelvins, and your answer would be, when divided, 2.6 liters. And this here is my Charles law experiment.
So this experiment here demonstrates Charles' law, which states that a gas expands as the temperature increases, and vice versa. A decrease in temperature will lead to a decrease in volume. And I've already had this running for a bit because it takes a while for the balloon to inflate. But the hot water, it's pretty hot on the sides, and then the bottle, and it involves a balloon, and it's already inflated a bit. But yeah, and this demonstrates Charles' law.
So my next law that I'm going to introduce would be Avogadro's law, which states that the equal volumes of all gases at the same temperature and pressure have the same number of molecules. So for a given mass, the volume and the gas are proportional if the temperature and pressure are constant. And some history on it was that Avogadro was the one that carried the experiments to demonstrate why the quantities of molecules in gas have the same volume. So gas could be derived from molecules or atoms. And the equation would be the initial volume over the first amount of gas in moles. So this equation involves moles, and then it's equal to the second volume over the second amount of divided by the second amount of moles. And a real life example would be blowing up a balloon, because you are adding gas molecules, thus decreasing molecules in your lungs while the volume of the balloon increases. And this link to YouTube would take you to some practice problems on Avogadro's law. And this question here correlates to Avogadro's law, because which states that a 25.5 liter balloon holding 3.5 moles of carbon dioxide leaks. So if I were able to determine that 30 grams of carbon dioxide were left in the container, what is the new volume of the container? So we're looking for volume, and this scenario is an example of Avogadro's law, because it deals with moles and displays it before and after, and you're trying to find a new volume. So the conversion would be from going to 30 grams to 0.68 moles, and this is how we did it, to go from grams to moles. So you would divide 30 grams over 44.1, which is the molar mass of the carbon dioxide, and you get 0.68 moles. And the equation would be 25.5 liters over 3.5 moles, equal to the unknown volume over 0.68 moles. And you would get, when cross multiplied, you'd get 17.34 liters over 3.4 moles, and your answer in liters would be 4.95 liters when you divide that. And that would be your answer for the new volume of the container. And this is my Avogadro's law experiment.
So this experiment right here with the balloon and the bottle of soda, the Coca-Cola, will basically demonstrate Avogadro's law. And his law states that the equal volumes of all gases at the same temperature and pressure have the same number of molecules. So for a given mass, the volume and the gas are proportional to the temperature and the pressure are basically constant. And basically here, if you were to shake the balloon, shake this, the Coke, the gas molecules move around, and so does the balloon. Basically, you can see it's inflating. So as we can see, as the volume of the balloon increases, the moles of the gas from the Coca-Cola are like adding up because of me shaking it. And so the pressure here in the balloon can be substituted to the volume of the bottle. All right, so increasing. Yeah, so this here demonstrates Avogadro's law.
So the next law we're going to move on to is Gay-Lussac's law, which states that the pressure of a given mass of gas varies directly with the absolute temperature of the gas. So the volume is kept constant, and pressure here is tied to the being equalized inside. And some history behind it is that Lussac first discovered that pressure of an enclosed gas is proportional to temperature, and he showed this by convincing evidence towards the relationship between pressure and temperature of a fixed mass of a gas kept at a constant volume. And this is a graph representation at the left about the pressure versus the volume. And the equation would be the pressure over temperature equals the second pressure over the second temperature, and in kelvins. And a real life example would be when, like a pressure cooker, like when it's heated, the pressure exerted by the steam inside the container increases. So the higher the temperature, the faster it's cooked. And this link to YouTube takes you to some practice problems of Gay-Lussac's law. And this question here correlates with Gay-Lussac's law, which states that a gas container is initially 67 millimeters of mercury and 87 kelvins. What will the pressure be when the container warms up to 80 degrees Celsius? So this is an example of Gay-Lussac's law because it demonstrates the before and after, and also contains pressure and temperature. So the conversions would be going from Celsius to kelvins. So 30 degrees becomes 303.15 kelvins. And these would be the variables here for the equation, the pressures and the temperatures. And the equation would be 67 millimeters of mercury over 87 kelvins, which equals to the x, the unknown value, so of the pressure over the temperature of 303.15 kelvins, which equals, when cross multiplied, it's 20,311.05 millimeters of mercury, and you cancel kelvins, and you divide it by 87, and your answer would be, for the second pressure, 233.46 millimeters of mercury. And this is my Gay-Lussac's law experiment.
So this experiment here will demonstrate Gay-Lussac's law, which states that the pressure of a given mass of gas varies directly with the absolute temperature of the gas. So it has to do with pressure and temperature. And so the pressure inside, we'll try to stabilize the pressure. And I'll be demonstrating this with candles, water, and a jar. And yeah, basically the jar will help to keep the pressure inside and equalize it. And the flame is slowly going away. And the water is also slowly rising. I don't know if you can see that. Yeah, it rose. It's rising. So yeah, the pressure inside is trying to stabilize with trying to equal with the outside. So yeah, yeah, this it demonstrates Gay-Lussac's law of pressure and temperature.
So the next law I'll be talking about is the combined gas laws. And what it is, it's basically Boyle's law, Charles' law, and Gay-Lussac's law all combined all into one. And it states that the ratio of the product of pressure and volume and the absolute temperature of a gas is equal to a constant. So a rise in temperature and pressure is basically the same pressure as the outside, as seen from the egg experiment, which I'll be demonstrating later. So the equation would be the first pressure and the second volume multiplied over the first temperature, equal to the second pressure and the second volume over the second temperature. And this video, link to the video will take you to the some practice problems on this law. And it's also equivalent to question number 6, because which states that a basketball has an internal pressure of 0.54 atmospheres and a volume of 7 liters at 30 degrees Celsius. So what will happen to the volume if a basketball were shot on Mars, where the pressure is 610 pascals and the temperature is negative 80 degrees Celsius? So this is a question here on combined gas laws because it utilizes initial pressure, volume, and temperature, and there's also an after and pressure, volume, and temperature. So the conversions would be going from 30 degrees Celsius to 303.15 kelvins, and then from negative 80 degrees you get 193.15 kelvins, and 610 pascals is equivalent to 0.006 atmospheres, which you get from dividing 101,325. And this would be the equation 0.544 times 7 and divided by 303.15 kelvins, which is equal to 0.006 atmospheres. And you're trying to find the second volume, and then you divide it by 193.15 liters. And then this is what you get after cross multiplying it. You get 735.5, like roughly 2, which is equal to 1.82, and you divide it by 1.82, so you could get the liters, which is the volume. So the second volume would be the 404.26 liters. And this is my combined gas loss experiment.
So this experiment here will demonstrate the combined gas laws. And what it is, it's basically Boyle's law, Charles' law, and Gay-Lussac's law all combined all together into just one. And it states that the ratio of the product of pressure and volume and the absolute temperature of a gas is equal to a constant. So we'll be demonstrating this today through an egg. We'll be using an egg, a boiled egg, paper, so a match, and then a bottle. So that it basically demonstrates how the rise in temperature inside here, because of the flame, creates the pressure outside more. So the egg drops in. you saw that. I had the camera angle a little out, but it went through. You can see the egg a little. So yeah, basically the pressure outside caused the egg to drop in.
So the last and final law we'll be discussing is the ideal gas law, and some history behind it was that basically a combination of the empirical Boyle's law, Charles' law, Avogadro's law, and Gay-Lussac's law. So the only difference between this one and the combined one is that it adds in the Avogadro's law, and which is includes moles, and it states that pressure and temperature and volume of gas are all related to each other, and the equation with units is the pressure and volume multiplied together equals N, which is the amount of moles, and the R, which is the ideal gas constant, and then temperature in kelvins. And this takes us to a video of practice problems, and this correlates with the question number 1, which states that what mass of carbon monoxide gas is contained in a 15-liter balloon at a pressure of 1,325 millimeters of mercury at a temperature of 36 degrees Celsius. And this problem is an example of an ideal gas law because it features no before and after, which is the main difference between this one and the rest of the equations, the laws. And then the conversions would be 1,325 millimeters of mercury, and you're going to atmospheres, so you get 1.74 from dividing, and that's how you get it from dividing 760. And then you go from degrees to kelvins, so 36 degrees Celsius would be 390.15 kelvins, and R, the gas, the moles, is 0.0821. And the equation would be 1.75 atmospheres times 15 liters equals N, which is a moles, and then the constant 0.0821 times 309.15. And then from that you get this. For multiplying each side, you get 26.1. And then for multiplying the other side, altogether you get 25.38 N, which is what you're trying to find, the moles. And you divide it by 25.38, so you could get the N by itself. And then you get 1.3 moles. And if you're going into grams, you cross multiply by its molar mass of carbon monoxide's molar mass of 28.01 grams to get grams. And it's equal to 28.85 grams. And that would be the answer, 28.85 grams, or if you want moles, 1.03. And this is my sources or my reference of where I got all my information for the moles, for the laws. And yeah, thank you.